Hi everyone, thank you for joining. My name is Kapil Pense. I'm a solutions architect with Amazon Web Services, and in this session, I'll be talking about anomaly detection in the context of log analytics, specifically with Amazon Elasticsearch service. Here's an agenda of what we are going to talk about. We'll start with an overview of log analytics, and the kind of data that we deal with in that space, and how Elasticsearch is a good tool to use with or for log analytics. Then we'll dive into understanding how machine learning fits into the use case of monitoring logs for specific patterns, and then we'll dive deeper into understanding how anomaly detection works, which is a new feature of the Amazon Elasticsearch service. I also have a demo for you and a few reference architectures that should help you get started. And I'll leave you with a couple of things that you should remember before you start building your own anomaly detection pipelines. So let's get started. Um, what is log analytics? Right, at a very high level, it's basically all about gathering all your logs, whether these are from your applications, from your IT systems, infrastructure, network, gathering all these logs, storing them in one place, and having the right tool set to analyze these logs in order to derive insights. And that also might involve ability to visualize and create dashboards and reports on top of this data. And the challenge with log analytics is really that the log data itself is very, very diverse in the sense it can come from many different data sources. These could be devices, these could be equipment on manufacturing floors. These could be mobile apps. These could be back-end IT systems, servers, network routers, other networking component. Um, these could be also applications that are generating logs, real-time data, web applications, business applications, container orchestration frameworks, and so on. And every such system produces logs um, that have their own sort of format and schema, and that can change over time, and there is no specificity that log data will always follow a particular schema. And um, you do need the right set of tools to analyze this data and make sense of this data. And your traditional or the typical tool set for doing data analytics is not always the best fit for doing log analytics. Um, for typical data analytics, you usually have a lot of transactional data, historical transactional data that you might want to run reports on, and you might be using things like relational databases or data warehouses to store and analyze that data. But when it comes to log analytics, you can't really use the same type of tool chain because usually traditional databases they can't really scale very well horizontally. And in the case of data warehouses, it's not possible to have, because they store data in a columnar format, it's not possible to have indexes on that in a way that you would need to investigate within log data. And with these type of databases or data warehouses, you need to define a schema for your data, and then based on that schema you can run queries. But with log data, like I said, there isn't any single schema that you can define. Oftentimes log data is is in the form of text strings, um, and fields might be missing. Fields might get added or removed from the data over time, and it's very dynamic in that sense. Uh, and you do need the ability to manually interrogate those text files or that text data. When you are looking at logs, developers might want to query logs for a particular time based on particular patterns or expressions. And all of that becomes really difficult with relational databases or data warehouses. Um, there is a better tool that really works very well with log analytics, and that is Elasticsearch. It's a data store. It stores your data. It can ingest your data in near real time. You don't have to have a specific schema on that data, and it also offers a very flexible and expressive interface for you to query the data, for you to filter the data, sort the data, and derive insights that you need. It also comes with a very nice visualization tool called Kibana for you to create those dashboards that you need. And it's pretty simple to use. It is a web application in the sense that it offers a RESTful API for all of its actions. You can send in the data in JSON format. So if you have text data, if you have a nested JSON type of log data, all of that can be easily stored into Elasticsearch by simply streaming the data and using its RESTful APIs. And it also provides a very easy to use API to search within the data once the data is indexed. And even the nested JSON fields are searchable as well. Um, the expressive nature of its query language extends to things like Boolean operations and filtering mechanisms that are very flexible. Um, Now, Amazon Elasticsearch service is a fully managed service which automates the creation and maintenance of your Elasticsearch cluster. Because, of course, with all the goodness of that software, you still need to have a production grade deployment of a cluster, and maintaining that at scale can be a challenge, which is where the Amazon Elasticsearch service helps you. It automates the creation and it creates a cluster within your own VPC or virtual private cloud, so that you can enforce your specific network and security rules that are appropriate for your organization. Um, it integrates with the AWS Identity and Access Management Service, so that you can control who has access to your cluster. It also integrates with Amazon CloudWatch and CloudTrail, so that you can see what's happening within your cluster, and you can have an audit trail of what actions were performed on the configuration of your cluster. When was it updated? When was it scaled? And things like that. Now, in order to ingest data into your Elasticsearch cluster, you can use the built-in integrations. For example, you could stream log data straight into your cluster from your containerized applications by having a sidecar with Fluentd or FluentBit that are streaming the logs into Amazon Kinesis, and then from there with Kinesis Data Firehose, you could land your data into your Elasticsearch cluster. You can also transfer data from other data stores into Amazon Elasticsearch service by using AWS Database Migration Service. And if you are streaming logs into Amazon CloudWatch logs, for example, with AWS Lambda, the logs by default go into Amazon CloudWatch logs. Over there, you could create a subscription filter on your log groups to automatically ingest all of those logs into your Elasticsearch cluster as well. Now let's look at what's really inside an Amazon Elasticsearch service cluster. It creates a load balancer which kind of fronts your cluster. And every time you're streaming data into your cluster, it's really going through this load balancer. Behind the load balancer is a set of different nodes. Of course, there are the master nodes. And for production deployment, we give you the option to choose dedicated master nodes, which do all the coordination of the work amongst the rest of the nodes. Then you have the data nodes, which actually store the data and run all your queries there. And then Amazon Elasticsearch service also has a new feature called ultra warm nodes. Ultra warm nodes, it allows you to create this storage tiering within Elasticsearch by storing data on Amazon S3. So all your data is actually when you choose to move it to the ultra warm nodes, the data is stored on Amazon S3. So it's much lower cost storage with the trade-off of slightly slower performance or higher latency data retrieval. But beyond that, everything remains the same. Your interface into the system also remains the same as if the data was within your Amazon Elasticsearch service cluster. Now, let's talk about machine learning in the context of logs. So, a typical centralized logging infrastructure like what we saw earlier, that lends very well to your needs around investigating past incidents, because all the data is in there and you're able to investigate, you're able to query that data to figure out what happened. But with machine learning, it's now possible for you to proactively monitor for anomalies in the data as it comes in. You can obviously monitor your log data and you can produce some metrics out of your log data, and you can configure threshold based alerts on top of that. But that type of an approach is not very flexible. Let me give you an example. You might have certain patterns in your traffic. So your users might be using your application mainly during daytime business hours, and therefore normal traffic levels might be at, let's say, 100 during the daytime. And then outside of the business hours, the normal traffic level might be somewhere around, say, 5. If you were to use a typical threshold based approach, you would need to set 2 thresholds and plus some kind of a time based activation of the different thresholds in order for you to receive alerts when traffic levels deviate from those normals. And this only gets more complicated with diversity in your applications. The more applications that you have, the more dynamic your traffic patterns are. It becomes really complicated to configure and maintain this type of a threshold-based mechanism for monitoring proactively. And this is where machine learning really helps you, because machine learning has a technique called anomaly detection, which essentially is the ability of the algorithm to learn from your data and understand what is considered or to be normal and what is considered to be not normal or an anomaly. And Amazon Elasticsearch service now offers such an anomaly detection feature, which is built around the random gut forest algorithm. And it's able to learn patterns in your data in real time, and it's able to output a couple of things. It's able to output an anomaly grade, as in how severe is the anomaly, and also how confident is the algorithm that this is really an anomaly of that grade. Based on that, you can easily configure alerts instead of having to configure and maintain several different thresholds. Um, we will look at that and how to set that up in a lot more detail. But before that, um, let's understand what are the different use cases where anomaly detection makes a whole lot of sense uh, for log analytics. Um, you could have, like I said, several different sources of data. Let's imagine you have VPC flow logs, you have S3 access logs, and you have your applications running in EC2 instances or containers, and all of those logs you're streaming into your Amazon Elasticsearch service cluster. Now, what are the few things that you might want to monitor proactively, and where machine learning based anomaly detection might make sense? Um, a number of things come to mind, but and this is not an exhaustive list, but things like an increase in error rates. That's really interesting. Like you might want to monitor, for example, the HTTP response codes from Amazon S3 access logs or your application logs, and on a normal day, of course, there might be some 400 error responses, but the in comparison to 200 responses, the 400 error responses usually are a much smaller number. But what if there is a sudden spike in those error responses? That's something you would want to monitor, right? And that's a good use case for using anomaly detection. Another interesting thing would be, imagine that your application is targeted towards users within a certain geography. Um, and you could use the client IP address to map it to, let's say, country codes that represent that geography. Um, now, if suddenly your application is getting a lot of traffic from outside of that geography, then that could potentially indicate a security concern, and that's something you might want to proactively monitor with anomaly detection. You could also monitor things like unusual changes in the amount of data that's being downloaded from your application, whether there is a certain spike in the amount of data going out, or there is a sudden drop in the amount of data going out. Um, that could indicate either configuration problems or potentially security risks that you should pay attention to. Similarly, certain changes in access, or rather access to your application at really odd times of the day, or a sudden increase or decrease in the amount of traffic that's getting rejected by your network configuration rules. Um, this, by the way, can be captured in the VPC flow logs. That could indicate, again, potentially problems with your network configuration, or potentially these are security risks that you should investigate further. So these are just some of the use cases where you might want to use anomaly detection. And now let's learn how anomaly detection actually works within Amazon Elasticsearch service. Um, as I said earlier, anomaly detection basically learns from your data. It learns to um, classify whether this particular data is considered normal, or is this a large deviation from what's considered normal and therefore should be flagged as an anomaly. And it doesn't require prior knowledge, as in you don't really have to have a labeled data set. um, the algorithm is an unsupervised learning algorithm, so it learns by itself over a period of time by looking at your data, and it learns to identify patterns. Like in the screenshot, you see I have a very consistent pattern here, and because my algorithm has been my anomaly detection has been activated and running on this data for a period of time, it has already learned enough. It has gained enough sort of confidence. So throughout these patterns, there is no um, there is no anomaly being flagged, because all of this seems to be pretty normal here and here. And the confidence score, which is the green line, is also quite high. Anomaly grade, which is the red line, is near zero, so there is no anomaly. But the algorithm has also learned to flag out as anomaly whenever there are deviations like this and this. And those do get flagged, like you can see here. This is marked as an anomaly. This was identified as an anomaly, and there were alerts that were sent out. Um, so all of this is part of your Amazon Elasticsearch service under the anomaly detection feature, and it works in near real time on your time series data by employing the random cut forest algorithm, which is baked into the service itself. Now let's take a look at how do you configure that and how do you use that. Um, the the most important concept to learn is something called a detector. When you want to use anomaly detection, you first configure a detector, and it's nothing but an individual anomaly detection task. Um, you configure this task with two parameters. There is a detector interval and there is a window delay. And the best way to understand these concepts is to visualize it on a time series. So here you have this is the current time, and this is your time series, and this is the data that's going to come into your Elasticsearch cluster. So if you set window delay equals 2, let's say 2 seconds, then that means the detector is going to wait from now plus 2 before it processes the data, which means it's going to wait for the time to be t plus 2 before it actually processes the data that came in at t, which is 0, right? And this is useful when you need a certain amount of time for some kind of a data pre-processing logic to run. Whether this might be some upstream systems that are immediately processing data that's coming into your Elasticsearch cluster, maybe reparsing the data or whatnot. So you might want to introduce such a delay. The second thing is the detector interval. Now, the detector interval is the amount of time that the detector accumulates all the data points for, and then runs an aggregation on top of that data to produce a single aggregate score. or a single aggregate value. Okay, so in this case, detector interval is 4 seconds. That means um, this detector is going to take or accumulate data for every 4 second interval, and then run some aggregation function on these 4 data points and these 4 data points and these 4 data points to produce single aggregate data points. The next concept to learn is something called a feature. A feature is nothing but a field in your data or in your index for which you want to learn what's normal and then detect whenever there's an anomaly in the values that are seen for that field. So building on to that visualization, now we have the detector interval configured. When you configure a feature, which could be a particular field within your JSON log packet, you also configure an aggregation function to be used to be applied over that detector interval. And out of the box, you can use aggregation methods like sum or minimum or maximum. You could also do things like a cardinality count. Um, and to give you an example, this could be back to the example of the HTTP response codes, right? You might be in your every log entry, you might be reporting what's the HTTP response sent out for this particular request from the end user. So you would see that on average, maybe 90-95% of your log entries would have response code is equal to 200, and then there might be a handful there which are say 401 or 403. So what you could do is you could run a sum on all the ones that are 200, and you could run a sum on all those that are 401 and a sum on all those that are 403. And those three things become features for your anomaly detection algorithm, uh, which means in this particular detector interval of say for let's say 10 minutes, there were X number of 200 responses, there were Y number of 401 responses, and there was Z number of 403 responses. Um, this is the data, these are the three inputs that are going into your anomaly detection algorithm, and that's what it's going to learn from. And over a period of time, it will learn to identify that, okay, on average, um, the error rates are between 3 to 4%, but anything more or anything less than that is going to be flagged as an anomaly, which is exactly what you want. Um, and then whenever it triggers or whenever it detects such anomaly, it's going to output a couple of things. It's going to output an anomaly grade, which is essentially like a severity score, like how severe is the anomaly. Um, and then associated with that is a confidence score, like how confident is your anomaly detection model in its prediction that this is a, let's say, zero point 0.7 grade anomaly. And the confidence is also expressed as a value between 0 and 1. So the higher the better. So now it's time for a demo. Let me switch to my browser. Okay, so here you can see that I have my AWS Console open, and I'm at the Amazon Elasticsearch service, and I have this Elasticsearch domain that is active with a version of Elasticsearch 7.4. So with that, I also have the Kibana console open here. Um, so let me quickly walk you through what's the kind of data I have within my console, within my Elasticsearch index. Um, so you can see that there is a number of fields already in my data that you would typically find in any sort of log files. I have the response code, I have the timestamp, I have remote IP, the number of bytes that were sent as part of the response to an application request, the URI that was requested, typical things that you would see in a web application log. I have also created some sort of additional fields in here as part of the data pre-processing that I applied to this. So from the remote IP, I've kind of mapped that to a country code and the status code instead of just handling or processing the value of that, which is typically 200 to 299 for positive or successful response, 400 to 499 for some kind of an error. Um, Instead of doing handling those values directly, I have done one hot encoding on this field. Um, so I have two binary fields which take the value of 1 for HTTP underscore 2xx if the response is 200, and it takes 0 value in that case. And alternatively, if there is an error and if the status code is in that 400 to 499 range, then this particular field, HTTP underscore 400, which takes the value 1, and this becomes 0. And we'll learn in a minute why this is useful. So let's go ahead and try to create a anomaly detection. Let's look at the console for that feature first. Um, so this is the dashboard, and here we can go ahead and create a new detector. Uh, let's do something very simple. We could either do anomaly detection whenever there is a sudden change in the error rates. Let's say there's an increase in the number of 400 errors. If that's what I wanted to do, I could configure a detector of this in this way. Select the index, and I also select the timestamp field. I don't wish to filter out any data, so I'll skip that. And I'm sending in data at a fairly high rate, so I'm just going to keep 1 minute as my detector interval and window delay. Go ahead and click create. It's not running yet. It still needs us to specify a feature, and here what I could do is um, use those two binary features that I created as part of the pre-processing. I could do, let's call it HTTP underscore 2xx, and that's the name of the feature. And for that, the input comes from the field in my data with the same name, and the aggregation function is going to be sum. So what this will do now is, because this field takes the value 1 or 0, if I run a sum on that over my detector interval of 1 minute, and if I have, let's say, 100 total entries within that 1 minute, is going to basically count the number of 200 responses out of those 100 total requests. and that could be, let's say, 95, and let's assume the remaining 5 were 400 responses. So if that's what I wanted to do, I could configure it in this way. HTTP 400 here. Select that field. Some is the aggregation method. I can do a preview because my index already has a lot of data, so I can see a preview of when is it going to flag anomaly. It's not going to be very accurate. The model has not really learned the patterns yet, but it gives you a decent visual feedback of what's going to be configured. Then I go ahead and click save and start the detector. Let's also go ahead and create another detector to simply um, monitor the number of requests that are handled by my application, and if there is any sudden deviation in that, let's call it request count detector. Once again, make these selections. Okay, that's done. Add a feature. Now, we don't really, if you recall, we don't really have a request count um, field, obviously. So what we can do instead is choose, for example, we could simply choose a field like a status code, and we could do a custom expression on that instead of just using the field directly. So what that allows me to do is, let me go back. Because this aggregation method list only supports these 4, instead of that, I could choose a custom expression and say, change this to another Elasticsearch aggregation uh, operator that I know exists, value count. So this is going to count the number of entries in my index within that detector interval which have any value for this field, and that essentially gives me the request count, because for every request there is always going to be a response status code, right? So with that, I can go ahead and once again run a preview. Here we see the request count. Like, I know my pattern and data is around maybe 75 minutes, so that does look correct. The request counts do really have these sort of traffic levels, so I can go ahead and get this going. Now, notice that the state changed to initializing. So error rate and request count is what I configured just now. It's going to take a while to train the model. Let's take a look at something that I had configured just a few minutes earlier, because I wanted to show you something interesting. It's running right now, but if you look at it's also configured to detect error rates on these 2 binary fields. And if you look at this, it has already kind of flagged some anomalies here, one here, but the green line is of interest because that's the confidence score. And even though it has flagged some as anomalies, because the model is still learning, it's still very fresh, it hasn't really fully understood the patterns in my data. So the confidence score is still quite low, it's only 0.6, but it is climbing up. So What I could do is I could configure alerts on this to receive alerts when there is an anomaly grade that is, let's say, higher than zero point 0.7 and accompanied by a confidence score of, let's say, 0.9 or higher. So that will kind of filter out all this noise. And let me show you what that will look like once I have a very stable sort of model running. Now, this is one that I have been running for more than 7 days. Um, and we'll zoom in here. Before I zoom in, you can see that. Well, let's go back to 7 days. Right. So here you can see my confidence score is now consistently high, and despite all these changes, there is pattern in here which the model has learned to detect and understand as normal pattern, and therefore there are no anomalies being flagged. But here there was an anomaly that was captured or detected. So if I zoom in on that to see what happened, you can see there is definitely a significant change from normal pattern, and that's why the anomaly grade was so high, accompanied by a very high confidence as well. So that's how this works, and let's switch back to the slides. Okay, now you can get started with anomaly detection for your logs. The first thing that you need is an Amazon Elasticsearch service domain that is at minimum version 7.4. So make sure you create a new domain or upgrade your existing domain to that version. And then you will get that anomaly detection feature in your Kibana console. With that, you can start ingesting your log data into the index. Like I said, make sure you pre-process your data if needed. Numeric fields are supported natively, but if you have categorical data like HTTP response codes, for example, or country codes, that type of data, or anything that's non-numeric, basically, that doesn't really work with anomaly detection. So you need to do some kind of a pre-processing on that to convert those into numerical values, or apply one-hot encoding to that. Once the data is started streaming into your index, configure your anomaly detection detector with those parameters that we learned earlier. And once the detector reaches a running state, once your detector is configured, you can also go ahead and configure when and how you want to receive alerts. The anomaly detection feature integrates with the alerting feature of Amazon Elasticsearch service, so you can receive alerts via Amazon SNS, Chime, Slack, or a custom webhook. Now, before you go, just remember that, like I said, this feature only supports continuous numerical features. If you have string data, non-numeric data, categorical features that's not natively supported, you might be able to work around that by doing some data pre-processing. So think about how you want to pre-process that data. Then the second thing is the values that you configure for your detector interval and the window delay. Those are really important values. Depending on what you set For those values, your detector could stay in this initializing state for several hours, because it's going to wait for accumulating at least um, a sufficient number of data samples. And remember that over one detector interval duration, it produces only one single data sample. So even if you have detector intervals set at 10 minutes, that would effectively mean in order for the algorithm to have sufficient number of data samples, several hours worth of data has to be processed. And this is where it helps if you have some historical data already in your index, because that data will also be automatically used. Um, if your detector stays in the initializing state for a very long time, like longer than a day, then you can actually use the profile detector API. So this anomaly detection feature has its own API, and you can use that API to kind of figure out what's going on, get some more information, and which allows you to troubleshoot your anomaly detection setup. And then finally, remember that this is a computationally intensive task, as with most machine learning tasks. So please do monitor the CPU utilization of your cluster nodes. And if you observe that the CPU utilization is becoming a bottleneck, please try to use larger instances that have beefier CPUs or more vCPUs. And with that, I'll take your leave. Thank you very much for joining this session. And I hope you can use today's learnings to implement your own anomaly detection pipeline with the Amazon Elasticsearch service. Thank you.